So thank you very much for the presentation and for the invitation. It's really an honor and a pleasure to be here talking today. So together with Franco, who is going to be the next speaker, we agreed both to talk about regularization by noise results. And so I will start with the somehow finite dimensional setting of SDs, and then it will move into the infinite dimensional one of SPDs. But let me start by saying, okay, this is a joint, what I'm gonna present is a joint work with Mategar and Cher from TUN. It's an archive preprint we put on last July. But for the sake of presentation, we'll start with some general considerations about regularization by noise as a whole. So, it's by now a very large field of research, but in a very broad sense, what regularization by noise is this idea that you take a system evolving in time and you try to understand if the introduction of noise into it actually allows to improve its qualitative properties. So again, this is very vague also because what are good properties and what are bad properties is a bit of subjective. But the most common exception, which is the one I will also stick with through this talk, is just to say you start with a system with might be post, might have multiple solutions or might not have any of them. And you're trying to understand if actually noise allows you to restore global existence and uniqueness of solutions. But just for the sake of culture, let me again specify this is not the only possible definition. There are other interesting phenomena which fall into the definition of regularization by noise, which are, for instance, the following ones, but which I will not treat here. And then there are many motivations for studying this. So mathematically, it's very fascinating because it's sort of paradoxical. You insert in your system something which is a priori bad in the sense that it's a very rough term in nature, but what it does is actually improve your solution theory and in some sense, smoothen out the system, at least in the sense that also the solution map that you get, like the data to output, will in fact get smoother somehow. And there is a driving principle behind this meta principle, which is the rougher the noise, the better the regularization. So in fact, even rougher terms should give you even better outcomes. But from the point of view of practical applications, the reason why it's important is because somehow noise is always there in any system, at least describing something that you can observe in reality. Because the point is either what you're observing, you observe it through measurements, which means there is a measurement error intrinsically when you do any observation, or even just at the level of whenever you write down a PDE or an ODE or any mathematical equation, this is through a simplification. You don't want to take into account, for instance, all particles of air you have in the atmosphere. You maybe just want to write down the dynamic for the relevant macroscopic quantities. But in doing so, you're introducing somehow noise into your system by means of all the terms you are not keeping track of, but which still in very small manner affect the system itself. And so all of this gives rise to the question, okay, noise is gonna be there, but how is it gonna be there? What is the correct way in which the noise should enter your physical equation, your model? And this is typically a PDE question. So I will actually leave the discussion of this point for Franco's talk. We will not really see it here, but I already want to mention, there are some general rules, so to say, as to how you should develop regularization by noise results. And finally, one motivation, which however, unfortunately, is very much open, but one of the reasons why it's interesting to try to develop this field of research and is where future research should go, hopefully, is actually to use noise as a mean to devise criteria for physically meaningful solutions. So what I mean here is that maybe your original deterministic system, for instance, could have multiple solutions, not a unique one, but it might happen that many of them are just mathematical artifacts, are not something you expect to observe in reality. It's just something which is produced by the mathematical treatment of the equation. And if you assume this, then you need to identify what are instead the actual solutions describing something interesting, which you expect to observe. And one possible way to do so is to say, okay, I first introduce my noise with an intensity epsilon in front of it. I try to push the limit as epsilon goes to 0. And the hope is that since the system with epsilon greater than 0 has a unique solution, the limit of these solutions might be unique as well, or at least might be a strict subset of all possible mathematical solutions. So you should identify some physical property solutions should possess. But as I mentioned, this is extremely open still nowadays. So we're really still back to the first step of saying for epsilon greater than 0, the noise at least, we can at least establish that noise provides regularization. And then taking epsilon going to 0 in the limit is still basically open. And as I mentioned here, we'll just focus in the simplest and most pragmatic case of finite dimensional SDEs. And in fact, my noise will also be of the simplest possible case, which is additive noise. And already this is a very much studied and very interesting example. So let me start by recalling you what is the well-known solution theory in the absence of noise. So if our drift B here is sufficiently regular, say Lipschitz, all life is fine, essentially. I mean, we do have existence and uniqueness of solutions. They also give rise to a Lipschitz solution map. We have everything, roughly speaking. But as soon as you try to go below this, things start to break down. So for instance, for any alpha between 0 and 1, strictly, you can find vector fields which are alpha order continuous, for which you have infinitely many solutions starting from the same point. So existence still holds, but we lose uniqueness. And if you go even below and you just take a drift, which is measurable and bounded, but possibly discontinuous, you can find examples of drifts for which no solutions exist. Yes, sorry, here is a typo. Here should be existence fails. And if you try to go even below, and now you take something which is just, for instance, of negative regularity, it's not even clear how to make sense of the equation, because you cannot just naively pointwise evaluate your solution along the drift, so you cannot make sense of this guy as a Riemann or Lebesgue integral. And already in the case in which your noise is, for instance, Brownian noise, is Brownian motion, it is by now well established that many of these pathologies can be cured somehow. So the most classical results by now are attributed to Zvonkin and Bertanikov back to the 80s. And they already show that strong existence and uniqueness holds whenever you take a drift B, which is measurable and bounded. So basically, noise allows you in all the first three regimes to achieve, roughly speaking, the same properties that originally only held in the first regime. And this has been refined by many authors. I mean, I'm gonna list all of them here, but basically you can even go beyond. It's actually even true for very unbounded drifts as long as they satisfy just some integrability assumptions, for instance, LQ in time, LP in space, that you can get global existence and uniqueness and a sufficiently regular flow map out of this. In the less regime, so alpha smaller than 0, is also known that there are results. I mean, the theory there is a bit more blurred. I will not go into detail, but there are classical works, for instance, by Bass and Chen. And there are also more recent ones, for instance, by Flandoli, Lucio, and Sorio, where they did show that you can get existence and uniqueness in low for suitable distributional value drifts. So all of this is to say, we already know that Brownian noise already allows to very much improve the picture with respect to the deterministic original one. But all of these results really did rely, at least in the way they're derived, on the Brownian structure. So one heavily develops the use of Ito formula, Ito calculus, and the relations to the underlying PDEs to the so-called Zvonkin transform or Ito Tanaka trick. But then there was another kind of result which came out, which was due to Davy, which tried to approach the problem from a different perspective. Basically, he said, okay, I mean, if my equation is with additive noise, at least if we assume, for instance, B to be measurable and bounded, the equation in integral form makes sense, I mean, without any notion of stochastic calculus. I mean, there are no stochastic integrals involved here. So in particular, what you could do instead is to say, let's just sample our noise term. Let's just fix the small omega term here. And the outcome now will just be a fixed realization, so a continuous path, essentially. And let's just look at this equation in integral form as basically just an ODE with random coefficients, where randomicity comes from the fact that I did sample this path here according to a certain law. Well, if you do that, then I mean, okay, maybe we cannot solve this, but it's clear that we can give meaning to this, if B is measurable and bounded at least. So we can at least define the random set of all possible solutions to this equation. And what Davy was actually able to show is that, and this is what is by now established as the first path-by-path uniqueness result in the literature. The terminology is due to Frankel, actually, it's not due to Davy. But what he showed is that P almost surely, with respect to the Wiener law, you can show that the cardinality of this random set is exactly 1, meaning there exists a unique solution to this equation. But I mean, really, the point is path-by-path uniqueness, at least morally, is much stronger than pathwise uniqueness. I mean, in order for a certain continuous function x to be a solution to this ODE for fixed random coefficient, you really don't need any measurability. You don't need any predictability. You even don't need an underlying probability space in principle. So it's really uniqueness among a much larger class of solutions. And it really tells us that regularization is really happening at a much deeper level, at the level of almost all possible Brownian trajectories, essentially. So if you now start following this line of thought, you do realize that at this point, you can really allow for the noise you insert in your equation to be something completely different from Brownian motions. Because really, there is no need for, Ito calculus or for those kind of considerations to enter the picture to some extent. And there are good reasons for wanting to consider different objects than Brownian motion. So for instance, in many applications, especially in finance and sociology, the properties of Brownian motion, like the fact that you have independent increments, are just basically too unrealistic. I mean, in many complex systems, we do expect that there is some memory dependence, that somehow people will keep track of what happened in the past. And so it's natural to work with noises which do have correlated increments, for instance. Another good reason, although more theoretical if you want, is the fact that Brownian trajectories are extremely specific. I mean, we do know that they are almost sharply 1/2 order continuous modulus logarithmic corrections. We do know that they satisfy the law of iterative logarithm and so on and so forth. So if you actually want to understand better what's going on at the level of regularization, especially if you want to understand what is the interplay, for instance, between the regularity of the perturbation and the effect it has on the ODE, really should allow us to have trajectories which do not have such very fixed properties, but which do exhibit a much broader spectrum of behaviors, essentially. And finally, as I mentioned, in view of Davis' result, I mean, Ito calculus should really not appear. I mean, the regularization in the Brownian noise somehow in the classical results comes through the Laplacian. But you now see that if you work at the trajectorial level, there is no Laplacian to speak of. So, I mean, properties like being a martingale or being a Markovian process, of course, are extremely useful. And I mean, it makes sense to use them whenever they're available, but shouldn't really be necessary in order to get these kind of results. And so there are some natural questions, and which I will try to touch upon in this talk, which is to say, I mean, can we, okay, characterize is too strong. Let's say, can we give sufficient conditions for some processes to show a regularizing effect whenever you introduce them in the ODE? And on the other hand, one should try to understand what are the best possible results we can hope for. How far can we push the regularizing effect as a function of the regularity of the process itself? And I will try to address them specifically whenever I sample W as a fractional Brownian motion rather than a Brownian motion, which now leads me to defining what or recalling what fractional Brownian motion is. So it's a fundamental Gaussian process. It's centered, and as such, all this law is entirely determined by its covariance. So there is a running parameter H, the so-called Hurst parameter, which ranges between 0 and 1, which determines the shape of the covariance function of the noise. But if you want to more concretely, fractional Brownian motion is this, at least in the one-dimensional case. So you see, it's a family of processes which, roughly speaking, all have the same shape, but they're all fractals, for instance, they're all spiky. But you also see that as H goes towards 0, these spikes become more and more frequent, more wilder, effectively, and also higher. And instead, as H approaches the opposite regime of being 1, they get milder and milder. So, I mean, the paths actually do get a bit more and more regular. So historically, it was first introduced by Kolmogorov in the study of turbulence, in fact. I mean, Kolmogorov really believed that some fluids should exhibit this kind of behavior in a turbulent regime. But nowadays, I mean, the modern definition is due to work by Mandelbrot and Van Ness, which also popularized fractional Brownian motion as a fundamental process. As I mentioned, the parameter H is related to how frequent and how violent, if you want, the oscillations are, which also we will see later is strictly related to the regularizing effect these processes have. And as the name suggests, is a natural generalization of Brownian motion, which corresponds to the regime h equal to 1/2, but it does lose some fundamental properties. So it's not a semi-martingale nor a Markov process. It does share other nice properties, which I will not need in this talk, but are still nice to mention, like Girshanov transform. So all of this is to say, this is a natural candidate to toy with, because on one end, it still has a lot of nice properties, it still has a lot of nice structure, but on the other hand, it doesn't have the most classical ones. So it really forces you to sort of go out of the comfort zone and stop using the standard techniques, and rather one needs to adopt different alternative approaches. But there is some hope to get something because we still have a lot of nice properties. And in fact, there are 3 fundamental properties which I will need in this talk and which are in this slide. But really what I'm trying to say is if you give me any other process which will satisfy the 3 properties in this slide, the results which I will present together with Mate will apply effectively. So the first one is just the fact that we do know that their paths have well-established regularity. Like for Brownian motion, we do know that fractional Brownian motion is almost sharply h-holder continuous, but nowhere h-holder continuous. Secondly, we know that it's self-similar, so which is also related to its fractal behavior and by why Mandelbrot was interested into it. But finally, and this is the most important property, this is a locally non-deterministic process. So what this means is if you try to compute the conditional variance of the process at time t, given all the history up to time s, this conditional variance is lower bounded by a multiple of the size of the interval t minus s to the power 2h. So more practically, this means that the increment wt minus ws will contain a component which is independent of all the past history, which is roughly speaking proportional to t minus s to the power h. So if you think about Brownian motion, this is perfectly obvious. I mean, in the Brownian case, the increment is effectively independent of the previous history, and this is just the covariance of the increment, so the variance of the increment. But in general, independence of increments will be lost whenever h is different from 1/2. But you can at least still say that there is an independent component, although it's not the entirety of the increment, basically. It also really means that these paths are intrinsically chaotic. You can never predict precisely where Wt will be, given all the history up to time s. So this concept of local non-determinism is extremely interesting on its own. It was actually introduced a very long time ago in the study of regularity of local times of Gaussian fields. It only entered the regularization by noise picture, I would say, between the last 5 years. I don't think it ever happened before that. But finally, let me mention, in my definition of fractional Brownian motion, I would actually allow for parameters h which are greater than 1. In fact, in the range 0 plus infinity minus the natural numbers. And this generalization comes through the most trivial definition. So I will just say fractional Brownian motion of parameter h plus 1 is given by the time interval of fractional Brownian motion of parameter h. But the reason why this is a good definition, at least for what I want to do, is because it preserves all of these 3 properties. I mean, for the new parameter h, these will still be enforced even when h is greater than 1. So, okay, having said this, I now want to explain at least heuristically what is the idea behind why fractional Brownian trajectories should regularize. And I mean, first results in this direction are actually from Nollart and Oknin, but really what I will present and what was a major breakthrough at the time is the work by Catellini and Gubinelli. So where they did show basically that there is a very robust framework where to understand these results, which comes through the setting of nonlinear Young intervals, which they also defined in this paper. So roughly speaking, the idea is the following. So we do know that fractional Brownian motion trajectories do have these oscillations. We saw it 2 slides ago in the picture. So now, if you assume we have a solution, assume for a second that the drift P is nice and everything can be solved, then the structure of the equation itself tells us that our solution X should be of the form of an integral term. So this more or less is something very regular in time, for instance, at least Lipschitz, if P is bounded, plus the noise itself, which instead is expected to be much rougher in time. So the idea is really the time scale where the oscillations of the fractional Brownian motion live should be a time scale where this guy stays almost constant, roughly speaking, which means that you can somehow think of this as a slow, fast decomposition of your system. So X being written as a slow component plus a fast one, which naturally implies that X should inherit all the extremely oscillatory behavior of W, assuming it has so. But on the other hand, if you now look at the slow component, what is very interesting is the slow component will satisfy a closed ODE. I mean, it's really just a change of variable, where now the fast component appears inside the integral. So the key idea is whenever you take time increments of the slow component, well, as I mentioned, if S and T are very close to each other, then inside the integral, you expect that you can freeze the slow component itself and only allow for the fast component to vary in time. And of course, this is a heuristic, but there is a way more rigorous way to do so, which is to say, whenever I take my increment theta t minus theta s, I write it down as a telescopic series, and now I apply this approximation at the level of each much smaller interval theta I plus 1. And in particular, these approximations should become more and more rigorous as the mesh of the partitions you take goes to 0. And now these guys take the form of some kind of generalized Riemann sum, which can be shown to converge rigorously to an object which is called, which Catalini and Gubinelli showed or defined to be a nonlinear Young interval. And what is one of the key realizations of the work is that in order to make this approximation step rigorous and to show that this guy is a nonlinear Young integral, the key information you need to have actually is not the regularity of B itself, but rather the regularity of a new object, which is the average field, which is this guy, TWB. So it is effectively defined as taking your original drift B, integrating in time along the noisy trajectory, basically. So it's really something that is defined in function of W and B, but not of the reference solution you're looking at, basically. So not only you can make sense of these intervals in this way, but in fact, assuming you have enough regularity of TWB, you can even show that this map, if you feed a function phi into it and you compute this nonlinear Young integral, this Riemann integral interpreted as a nonlinear Young integral, it will map functions of finite p variation with p smaller than 2 into functions of p variation, and it will do so in a Lipschitz way. So at the end of the day, what you can really do is you can set up a fixed point argument for the slow component, exploiting solely the regularity of the average field TWB. And in this way, you can deduce existence and uniqueness of solutions. So all of this is perfectly fine, but the next realization in the work, and what really becomes a bit miraculous in some sense, is the fact that this prescribed regularity which you need to have for the average field TWB, in many situations, depending on what are the parameters you're working with, actually is an object which you can probabilistically construct and show to be regular, even when the original drift B you were starting with is distributional. So the point is really, we started with an ODE, which we could reinterpret equivalently in the case where B is moved as a nonlinear Young or the differential equation, but now the new interpretation is more robust than the original one. You can now find situations where the original ODE doesn't make sense anymore. If B is distributional, you cannot give meaning to the Riemann integral, but you can still give meaning to the equation and solve it analytically once you enforce instead the new generalized notion of nonlinear Young differential equation. And at the end of the day, what this allowed the authors to prove, Catalini and Gubinelli, is that if you give me any h between 0 and 1, and any drift B, which is alpha Holder continuous, here C alpha will be a Bezow-Holder space, actually. So it's, if you want B alpha infinity infinity, under the assumption that alpha is greater than 1 minus 1 over 2h, you can show that the equation can be solved, and in a very strong sense. So strong existence and path-by-path uniqueness, which is this concept a la Davy, will work for the equation with the fractional, driven by the fractional Brownian motion. And so this relation now is super nice because on one end, you see that for any fixed parameter h, you can find alphas strictly smaller than 1, which satisfy this relation. So you can find older continuous trees for which uniqueness would fail without the fractional Brownian motion, but which will be true with fractional Brownian motion. On the other hand, as h goes to 0, this right-hand side here becomes minus infinity. So this tells us two things. I mean, no matter how ugly the original drift E, no matter how bad the space it leaves is, you can find a noise regularizing the equation and for which the equation is meaningful. And on the other hand, it does provide a quantitative version of the paradigm, the rougher the noise, the better the regularization. So, I mean, if you measure roughness through the parameter h, the smaller h gets, the larger is the set of alphas which are allowed by this relation. So all of this is extremely nice. And one of the key strengths of this approach is that it's really somehow a rough path approach in the sense that it splits entirely the probabilistic and the analytic step. So if you give me any perturbation W, all you need to check is that by stochastic estimates, you do have the regularity of the associate average field, TWB. But once you've done that, you can entirely run the nonlinear Young machinery, which is basically just applying the Swin lemma. It's an entirely analytic argument to solve the equation analytically. So again, this is extremely nice, and still nowadays it has been revisited several times. I mean, there's still room for improvements, for instance, by Arang and Perskowski, and also by myself and Massimiliano. But at the same time, this clean separation is also, if you want, the major limitation of the approach. Because the point is really, I mean, when you try to really go for sharper results, having a clean cut between these two steps becomes more and more expensive somehow. So for instance, this approach will not work if you try to deal with h greater than 1, although this is in principle, this formal relation will still be meaningful and will still be useful. And also, for instance, it makes it harder to work with time-dependent drifts and so on and so forth. I mean, again, there are many small details, but it's just to say, I mean, it's not so obvious that it's really nice to maintain this clean separation. So the question, the natural question, which I want to partially address here is, can we actually sort of not do this clean separation, keep both the probabilistic and analytic approach, and see if this allows us to get something better? And the answer is partially positive.
Sorry.
Yes.
There's a question in the chat. Maybe.
Sorry, it's because the full screen, it's hard to see
the question,
chat.
I can read it. It's asking what is C alpha for negative alpha?
So, I mean, the rigorous definition is through Bezow spaces. So, which can be defined in many ways, but roughly speaking, I mean, you should Google it. If you want a more down-to-earth definition, if you take alpha greater than 0, and if you have a function which is alpha order continuous, its derivatives will be alpha minus 1. So the idea is something is, for instance, of regularity C minus n. If applying n antiderivatives, you get out something continuous. And I hope that gives a sufficiently intuitive definition. So I guess I will.
Yeah, you
can. Sorry, C alpha is distribution or function for negative alpha?
Yes.
What is it? Distribution or function? Real function?
No, it's a distribution.
Okay, thank you.
Welcome. Okay, so as I mentioned, the results can be partially improved, but in order to do so, I mean, the first question is, I mean, why should we not expect the Catalan-Guminelli result to be optimal somehow? And there is a nice way to see this, at least, I mean, that predicts that they shouldn't be optimal by running a scaling argument, basically. So we do know that our noise, W, is subsimilar. We can try to apply the same scaling transformation that under which the noise is stable in low to the solution of the SDE. And what happens if you try to do the same scaling transformation is that the transformed solution will satisfy an SDE with exactly the same structure, only now the drift was also rescaled accordingly. And what you can now ask is to say, assume my drift live in a certain regularity scale based on a norm of a Banach space. Let's see how that norm behaves under this rescaling. So for instance, here we'll take some regularity, which is of the form LQ C alpha. What I mean here is LQ in time, C alpha in space. And if you try to look at how this behaves, well, the scaling acts as a power law in terms of the norm. And this allows us, heuristically speaking, to identify the subcritical regime as the one where this exponent is basically positive, which gives us this relation, alpha greater than 1 minus 1 over HQ prime, Q prime being the conjugate of Q. So what is the heuristic behind this argument? When you are rescaling, what you're doing is really looking at what your solution is doing very shortly in time on very small scales. And so the hope, if you want to see any regularization, is that at this very local level, the noise should win over the nonlinearity. I mean, if the nonlinearity were winning over the noise couldn't do anything, basically. We shouldn't be able to see any regularization. We should see the same pathologies as for the original equation. So in this regime, which is the one where the noise is locally winning, you do expect to, at least in principle, to be able to solve the equation thanks to the presence of the noise. But again, let me say, this is very heuristical. I mean, even in the standard Brownian case, if you try to apply this argument for Q equal to infinity, what it spits you out is going to be C alpha for alpha greater than -1, which is still not entirely settled. So again, this is just a roadmap saying this should be the correct relation, which is different than the one that Catellier and Gubinelli get, which is 1 minus 1 over 2h. And with this, I can now present you the result we obtained with Mate. So this is basically telling us we can, in fact, cover certain portions of the subcritical regime. So if you give me now any parameter h between 0 and plus infinity, and you look at the equation for a certain given b, which is now q c alpha, I will be able to solve this SDE now under the condition that alpha is greater than 1 minus 1 over HQ prime. So this is exactly the subcritical regime, and the additional condition that Q is between 1 and 2. And this instead just comes from the techniques we use. So in this case, we can solve the equation in a very strong sense, the sense that we can also understand a lot about the behavioral solutions. So first of all, we can establish existence, pathwise uniqueness, and path-by-path uniqueness a la Devi for this kind of equation. Next, we can actually show that it admits a stochastic flow of diffeomorphisms. Here, I really mean stochastic flow in the sense of Kunita. I mean, the solution map will be jointly continuous in time and space. It will be differentiable in space with differential, which is jointly continuous in time and space. And as a function of space, it will be invertible with inverse that has the same properties. And all of this sentence holds P almost surely. Moreover, we do have stability estimates. So basically, what we have is that the solution map that do the initial datum and the drift associates the outcome solution is locally Lipschitz. In particular, it's locally Lipschitz in the sense that you can measure the distance between two outcomes in the supremum norm in time and taking any moment P of arbitrary order. And what is also nice is the way in which you should measure the distance within the data of the problem is actually a weaker topology in the drift than the one needed for solvability. So for solvability comes in LQC alpha, but then stability will come in LQC alpha -1, which is a weaker distance. And let me say all of this is also very useful. Well, first of all, it gives us a sanity check. I mean, it tells us that any solution we construct in this way is the unique limit of the solutions we would have obtained if we modified the drift and send the modification to 0. But it's also quite important for numerical schemes. So what I'm saying here is, if you want to simulate a singular SDE, you cannot do this directly because, I mean, if the drift is singular, you cannot pointwise evaluate it. So you really cannot run an Euler-Majorana scheme from the start because it might generate immediately too unstable and too big errors. So what you actually might want to do is to say, let's first modify the drift and now run the scheme for the modified drift and hope that this procedure, I mean, doesn't produce such a big error. So the first approximation by modifying the drift is something that you can control with these kind of estimates. Now, I have another slide of main results, again saying what we can understand of this equation. So this previous slide was about the SDE. This next point, D, is actually about a more complicated situation, which is the one of distribution-dependent SDEs. So we're able to solve them as well. What I mean here is that the drift will not depend only on the solution X itself. It will also depend on the law of the solution itself. So it's somehow a non-local interaction in the probability space, if you want. We're able to solve these kind of equations under the assumption that our B is of convolutional type, is a McKean-Vlasov type of drift, which is defined in function of two functions, f and g, which correspond, roughly speaking, to a potential and a pairwise interaction kernel, as long as they do satisfy the same regularity assumptions as from the previous slide. Next, I will not go into this, but I still want to mention very quickly, we can show that solutions are Roy irregular. So Roy irregularity is a concept that Catalian and Gubinelli introduced in their paper. In my opinion, criminally underrated. I think it's a super interesting concept, but it is known that fractional Brownian motion is Roy irregular for any rho smaller than 1/2h. Here we show that the solutions have exactly the same property. So again, it's following this philosophy that solutions are inheriting the same behavior as the driving noise. Under weaker conditions, we are able to show by compactness method that there exist weak solutions. Specifically, this is true, for instance, if B is in L infinity C alpha, for alpha now greater than 1/2 minus 1/2h. Unfortunately, in this case, uniqueness is entirely open. But still, I mean, there is some room for further conditions, so to say. And finally, we are not able to establish the positive side of the full subcritical regime, because I told you have this restriction that Q has to be between 1 and 2 in our results. At least we can establish the negative side. So we can rule out that we cannot do better than this, than what is predicted by the scaling argument somehow, because we can produce examples of drifts which are LQC alpha with alpha smaller than 1 minus 1/HQ prime, such that at least one between uniqueness in low or pathwise uniqueness has to fail. So there is some truth to the heuristic of the scaling, which suggests a subcritical regime, but it's not so clear how much truth there is. Well, there is still some open section. And having said this, I want to shortly compare this result to what is known in the literature, but really a very short comparison. So as I mentioned, the baseline result is by Krylov and Rockner. Sorry, here is a typo. This is 2005. So they showed existence and uniqueness when B is LQ LP under this condition. So 2/Q plus D/P being smaller than 1, and P and Q being between 2 and plus infinity. Well, actually, it turns out, I mean, these, if you replace LP with the corresponding Bezov space, which is Bezov-Holder space, which is C minus D/P, this is exactly the subcritical scale. So it's nice to say, it's nice to compare that there are already other results in the literature which did, in fact, confirm the validity in some special cases of the subcritical regime. And in fact, and this is much more recent, now even in the Brownian case, even the critical case is now settled, at least for LQ-LP drifts. But on the other hand, if you really look into C alpha drifts, much less is well understood. So the subcritical, the scaling argument will give us the condition alpha greater than -1. What is clearly well established is that we can cover alpha greater than -1/2, actually. And if you want to go beyond that, there are many works doing that, but under more and more refined conditions on your drift B. I am not aware of any result which treats fully general drifts C alpha without any further assumptions for alpha merely greater than -1. Another thing, let me mention our result in the regime, so my result with Mate, in the regime where Q is smaller than 2, seems to be new even in the Brownian case. Admittedly, I mean, and I'm happy to be wrong about this. If anybody knows references, I'm happy to hear them. Admittedly, I think this is just because people really didn't look a lot into this regime. I mean, usually people are more interested into trying to push the space regularity down, so actually getting to a more and more negative space regularity. They're not fully interested in trying to put the integrability in space in time to be weaker. But this Q smaller than infinity is outside of the Krylov-Rockner class, and it's something we can cover. So it's just to say, it's nice to see that alternative techniques also shed some new light on what should be going on in the Brownian case. Then, okay, in the fractional Brownian case, as I mentioned, so the benchmark is alpha greater than 1 minus 1/2h. This was established by Catalian and Gubinelli. And then Mateger and Cher, in his own paper now published in 2022, was able to show that this exact condition still holds true also in the regime H between 1 and plus infinity. So our result, due to the restriction Q between smaller or equal than 2, does not improve on the space regularity threshold. I mean, Q smaller than 2 actually enforces that 1 minus 1 over HQ prime is always greater or equal than 1 minus 1 over 2H. So what we're really improving here is that we are weakening the time regularity condition, not the space regularity one. And improving the space one is, in fact, very much open. There are some results which at least do reach the non-critical, but still extreme, I mean, not critical by scaling, but extremely difficult to reach, equality alpha equal to 1 minus 1 over 2H. This was, for instance, done in the paper by Atreya, Butkowski, Le, and Mitnick, and then another one by Anzaletti, Richard, and Chanre. So having said this, now I want in the remaining time to present you what are some of the key ideas in the proof. So the first tool is the stochastic swing lemma. I will specify it more in the next slide, but let me just mention it was first introduced by Coalet in 2020, and there are now many versions for it. And the way it enters our picture is by trying to define intervals of the following kind, in the case where F is a distribution of negative regularity. So again, it's sort of the same game Catalino Gobinelli played of sort of making sense of the average field, but now I do not want to split the probabilistic and analytic step. I really want to have a concept for theta, which is an analog of being stochastically slowly varying in time. And the second key ingredient, which exactly answers what is the correct definition for this concept, is a refinement of a key intuition from the work by Mate, which already did essentially establish what are the correct a priori estimates you need to develop for these SDEs. What are really the natural properties you should expect to see your solutions having. And it's a bit of a technical property, but it's of the following form. So let me try to guide you a bit through the definition. So we take our slow process theta at time t, and we now try to compare it to its best prediction given all the information up to time s. Now we take the modulus, so the error we commit by this approximation, and we try to understand what is the best, what is the expected error we do with this approximation, again, given the information up to time s. So all of this is random variable, and now the property that one can show is that this is actually uniformly bounded in probability by just a deterministic function of the size of the increment st, which is of the form t minus s to a certain power, times a control, which is a super additive function, is a concept which appears very naturally in rough path theory, to the exponent 1 over q. What is important to observe here is that this exponent alpha h plus 1 over q prime is, by the subcritical regime condition, strictly greater than h. So the idea is really this guy is slowly varying compared to the fractional Brownian motion, because fractional Brownian motion oscillates at a time scale t minus s to the power h, while instead here we get a higher exponent than that. And let me also mention a somewhat similar condition, although not identical, also appeared very recently in a preprint by Coalet, where he introduced a class of bounded mean oscillation processes. So again, there is something, going on here, which is not yet completely understood, and it's interesting to explore on its own. But as I mentioned, the other key ingredient is stochastic swing lemma. So it's a refinement of the classical swing lemma from rough path theory. So the idea is in in the swing lemma, you are given a family of local approximations, and you try to construct their suing, so the unique path whose increments are very close to these local approximations. And you can do this under a certain, let's say, consistency condition on this family, which is usually expressed in the following way. But if you deconstruct the proof of the standard swing lemma, you end up realizing that's really just using somehow convergence of geometric series and triangular inequalities. And the key intuition Coa had when he developed the stochastic swing version is that you can somehow use less rough estimate. You can, instead of triangular inequalities to check that certain series converge, you can now use stochastic cancellations, and these come by means of martingale inequalities instead. So the idea is, instead of this consistency condition, what now suffices is to know that these local approximation A of ST are roughly speaking of order t minus s to the power 1/2 plus something. Again, this is the control, but think of it as just being t minus s if you don't know what controls are. And now the stronger part of the consistency condition is not posed on delta A anymore, but on the conditional expectation at time s of delta A. And the hope is conditional expectation is introducing some cancellations. And so this condition is effectively weaker than the original one. So like Swin lemma, one of the advantages of stochastic Swin lemma is that it's extremely elastic. I mean, given the problem you want to tackle, you can tweak around with it and you can try to sort of partially change both the hypothesis and the outcome to suit the problem you're dealing with. And this is what we did in our case. So we went through the same proof, but now instead of applying the same martingale inequality that Koa used, which is bulk orders inequality, we did apply Azuma-Effding's inequality. And so the idea is that if you now start with a stronger assumption, which however we can verify in the cases of our interest, in particular, you now have L infinity bounds in the probability space and impose, roughly speaking, the same assumptions as before, the outcome is that you can still correspondingly construct your stochastic Ewing, so the unique process whose increments are roughly speaking close to A of ST. And the advantage now is that what you get is Gaussian tails for this guy, which is sort of natural if you think in terms of martingale bounded increments have Gaussian tails. But it does have Gaussian tails, and also what is inside this exponential squared is actually a modulus of continuity for A. Which also entails the fact that this guy has finite p variation for p smaller than 2. And with these ingredients, I can now give you a sketch of the proof of the uniqueness part of the SDE. So remember, assume I've given a solution x, theta plus WH, I know that theta will satisfy the a priori estimates, encoding the fact that it's slowly varying in time. And on the other hand, WH is locally non-deterministic. So I can never predict it given a history up to time s. If you combine these two informations with the stochastic Ewing, you can define rigorously processes of the form integral in time of f of s, x of s in the S, even when f is now a distribution. And in fact, you can do this if f is LQ in time, C beta in space, for beta greater than -1 over HQ prime. And once you do this, the resulting process is also going to be a finite p variation for some p smaller than 2. If you want, you should think it's morally gamma order continuous for gamma greater than 1/2. Now, if you're given two solutions, you can run this argument for both solutions. And on the other hand, you can try to compare them directly. So if you do so, the noise is additive. So it will cancel whenever you compare the two objects. And you're left with the two different integrals with respect to the same drift. What you can do now is to say, well, let's just take, I mean, roughly speaking, of course, this is a simplified argument. It's a bit more rigorous than this. You can tailor expand around one of the two, basically. So you can say the difference of these two guys should be, roughly speaking, gradient of B evaluated in one of the two times the difference of them. But the point now is really, given our original assumptions on B, gradient of B satisfies the assumption here. So we can actually make sense of the process given by the integral in time of gradient of B along the solution x1, which is going to be a finite p variation. And so the point is really, you should think of these guys not being a pointwise multiplication, but rather being x1 minus x2 times the time derivative of the integral in time of this guy. And if you enforce this interpretation, you actually realize that this last equation is now a linear Young differential equation driven by an object Z, which is a finite p variation. And this is now for p smaller than 2 is a perfectly well-defined Young regime, which is well known and for which solutions are known to be identically 0 if they start from 0, which at the end of the day tells us that the two solutions x1 and x2 will coincide. So, okay, this concludes all I wanted to say about the ideas in the proof. I still have one slide of open problems, but I think my time is up. So I will just leave it for the audience and I will stop here.
All right. So thank you, Lucio, for that very clear talk. So everyone can clap however they would like. So we do have a little bit of time for questions. Feel free to unmute yourself or type them into the chat.
Sorry, in this Ewing lemma, there was some function W of TS in estimates. What is it? Yes, WST.
Yes. So yeah, sorry, that's what is usually called a control. So controls are a natural generalization of the most basic function modulus of T minus S. I mean, they're closely related to the notion of finite P variation, and they're basically positive superadditive functionals, I think, and satisfying the property that on the diagonal they're zero. So WSS has to be zero, and WSU plus WUT is less or equal than WUT.
Mm-hmm. Thank you.
Welcome.
Lucio, may I ask one question?
Absolutely.
Hi. Basically, maybe I will shoot wrong, but can this analysis in terms of the uniqueness be studied separately, as you mentioned, for different values of alpha? And is there any phase transition? Would this help in any way? Maybe I'm shooting wrong, but could this be studied as a phase transition with the alphas in terms of the different bounds and so on?
This is a very good question. I don't know, to be honest. So in the Brownian case, which is the one where most of the literature is by now settled, I would say there is a very clear discriminant. This is a very nice argument that has been developed by several authors, but I think you can find it in the paper by Beck, Flandoli, Ubinelli, and Morelli. So basically, so let me just go a bit back. In the Brownian case, the most understood case is the Krylov-Rockner regime, which we now also know to hold, I mean, with some more specifications in the critical equality. So up to critical equality, roughly speaking, we do have strong existence and pairwise uniqueness of solutions. If you go into the opposite regime, so where now it's supercritical greater than one, there are some explicit examples where simply you can show that solutions cannot exist, or at least cannot exist globally in time. So really, it seems like either you get everything or you don't get, or you get nothing. There really doesn't seem to be any intermediate behavior between any of these. But again, I mean, these are very specific examples we are talking about. If you start doing more assumptions on B, for instance, what the divergence of B is doing, the picture might be completely different. So on that, unfortunately, I don't have a precise answer.
But this, your proof of uniqueness holds in general or only in certain regions of alpha? I didn't get this clearly.
Sorry, yes, it works in this regime.
Only in this, okay, yeah, thanks.
Yes.
Thanks.
Yeah, we probably have time for one more question or so.
Maybe just out of curiosity, I mean, so you develop everything for the fractional Brownian motion, which in principle is, I mean, the general, I mean, the Gaussian process. Do you really need all the properties of the fractional Brownian motion, or could you just say, okay, I take a general Gaussian process with the covariation structure, and then I, depending on probably the regularity of this structure, I can go through your whole approach and get something out?
Yeah, so roughly speaking, at least morally, the three properties I need are the following ones. But I mean, in fact, actually here I'm cheating a little bit. So I did use self-similarity in the heuristical argument to have an educated guess about what is the correct subcritical scale. It does never enter in the proofs. So really the two properties I need are A and C. And actually you should really think about this as just being a double bound on this guy. So what I should need, roughly speaking, is to know that this is greater or equal than something times t minus s to the 2h, but also lesser equal than something times t minus s to the 2h. I think effectively that's all we need in order to run the analysis. Because somehow it's providing us both the a priori bound on theta and the local non-determinism, and then we just plug in the stochastic Swing machinery, so to say. So in that sense, if you give me any other Gaussian process, I mean, as long as we're talking about Gaussian processes, if W was not Gaussian, this wouldn't be the correct condition to work with. But as long as it's Gaussian, it's basically a double bound of this type. That's all we really care about.
Thank you.
Okay.
All right. So thanks again. We'll go to our